Welcome to online Algebra 2 class. Today we are going to be doing section 6-5, solving square root and other radical equations. Okay. So our objective is to solve square root and other radical equations. Okay, and we can do this. We can solve these by undoing the previous operation, right? Undoing the radical by mostly squaring both sides. And when you do that, when you square both sides of an equation, it's possible for us to have something called extraneous solutions. Extra solutions. Solutions that don't solve, that don't actually work to solve the problem. All right, so what is a radical equation? Very simply, a radical equation is an equation that has a variable in the radicand or a variable with a rational exponent. So a variable inside of a radicand, right, underneath a square root, underneath a cube root, or to a fractional exponent power. Okay, so all those are radical equations. And if the radical has an index of 2, like that one, then that is called a square root equation. So in this lesson, in this section, we're going to assume that all radicals and expression with rational exponents represent real numbers. So that means we're not going to get any imaginary numbers. So that means we could also assume that all the variables are positive under the roots, which means we don't need any absolute value signs or anything that we did in section 1. Okay, so to solve these radical equations, we very simply have to isolate the radical on one side of an equation. Then undo the radical by raising each side to the power suggested by the index. Raise each side to the second power, raise each side to the third power. We'll get to that one, but a little different. Let's start with a square root equation, right? So solving the square root equation, my first thing that I want to do is I want to isolate the radical. I want to get that thing by itself. Okay, so subtract 3 from both sides. So that leaves me with the square root of 2x minus 3 is equal to 5. Okay, now to get rid of the square root, I raise both sides to the second power, the same as my index. So this turns into 2x minus 3, and it's equal to 25. Okay, very simple to solve the rest of these. Add 3 to both sides. So 2x is equal to 28. Divide out the 2, and we're left with x is equal to 14. Okay, again, isolate the radical, use the index to raise both sides to that power, and then solve the remaining equation. Okay, let's try a got it problem. Okay, isolate the radical. Don't do this, can't do that, right? Because that's really not a 1, that's underneath the square root. What we can do, however, to isolate the radical is add 5 to both sides. So let's put this over here. So that's 4x plus 1 underneath my square root is equal to 5. Square both sides, and we get 4x plus 1 is equal to 25. Squaring a square root undoes the radical and makes it go away. Subtract 1, 4x is equal to 24, so x is equal to 6. Okay, next, the fractional exponents, right? My rational exponents. So to solve equations in this form where we have a rational exponent, we're going to raise each side to the reciprocal of that exponent. So we had on the first page there, we had x to the 3 over 4 power. In order to make that go away, I raise it to the 4 over 3 power. Because then, power to a power, we multiply those exponents and they turn into a 1. However, if either one of these numbers either one, it doesn't matter which one, if either one is even, we have to do this. Because when we raise a negative number to the fourth power, right, that negative actually goes away. So there could be possibly two solutions to this. So if we remember how to solve the absolute value equation of x, if we have something like that, we split it into two separate equations. Okay? Because inside of here could be a positive 2 or a negative 2. Okay? Let's see what I mean by this. Okay? First, isolate the radical. First, divide out the 3. So we have x plus 1 to the 2/3 is equal to 4. Now, I'm going to raise both sides to the 3/2 power. Okay? These cancel. That was the point. So x plus 1, remember the bottom is a root, the top is an exponent, so the square root of 4 is 2. 2 to the 3rd power is 8. But was one of those numbers even? Yeah, the 2 is even. So that means that this is not the answer. It must be the absolute value of x plus 1. Okay? Which then turns this into two equations. The positive case and the negative case. So subtract 1 from both sides, x is equal to 7. Subtract 1 from both sides, x is equal to negative 9. Okay? And this does work. Even the negative works, right? If you plug negative 9 in here, right, we have negative 9 plus 1. That's going to be negative 8. The third root of negative 8 is negative 2. Squared is a positive 4. Times the 3 is a positive 12. Okay? So this does actually work with both of these numbers, with the positive and the negative case. Let's try this one. Isolate the radical first. Subtraction first. So that's 3 times the 5th root of x plus 1 to the 3rd power is equal to 24. Divide out the 3. That is the 5th root of x plus 1 to the 3rd power is equal to 8. 5th root, 3rd power, that is x plus 1 to the 3/5. And I just rewrote that in exponential form. The root goes on the bottom, the exponent goes on the top. In order to clear it out, I raise it to the 5/3. Root first for this number, the third root of 8 is 2 to the 5th power, 2, 4, 8, 16, 32. So x plus 1 is equal to 32. Now, both of these are odd, which means I do not need any absolute value signs. Okay, so we get 31. Okay, let's try a guided problem. Ooh, one of them is even. Okay, so I'm going to need absolute value signs here. So divide out the 2. So we have x plus 3 to the 2/3 power is equal to 4. And then raise both to the 3/2 power. To cancel that, I need absolute value signs. Square root of 4 is 2 to the 3rd power is 8. So x plus 3 is equal to 8. And x plus 3 is equal to negative 8. Subtract 3 from both sides. X is equal to 5. And x is equal to negative 11. Okay. So, Meteor Crater, if anybody has seen this before, it's been in a lot of movies. Thor, the first one. For the Meteor Crater in Arizona, the formula for the volume relates the volume to the diameter, and it is the diameter is equal to 2 times the third root of the volume over 0.3. Okay, what is the volume? Here's the um, what do you call it, diameter, right, from end to end. So we can very simply solve for the diameter, realizing that 1.2 kilometers is 1,200 meters, right, in cubic meters, right? We want to change to meters. So let's use my formula, and let's make sure I know how to solve this. So 1,200, the diameter, is equal to 2 times the cube root of the volume over 0.3. Okay, divide out the 2. We get 600 is equal to the third root of the volume over 0.3. If I want to get rid of a third root, I raise both sides to the third power. So, third power, 600 to the third power is going to be a rather large number, 216 million. It's okay. Is equal to V over 0.3, and then I just multiply both sides by 0.3. And we get that the volume of the meteor crater is 64,800,000 meters, cubic meters. Should have left it in kilometers, right? Then that would have at least been, only 64,000 kilometers. Okay, but the point of this problem was not to go crazy with the numbers here. The point of this problem is just to understand that if you have the equation, okay, if you have the equation, right, all you need to do is plug the numbers in and get the desired variable. Okay, so when you raise each side of an equation to a power, it's possible to introduce extraneous solutions. Extra solutions. Therefore, it becomes very important that you check all your solutions in the original equation. If your solution works, it will give you something that's true, like when we checked it before. An extraneous solution will give you something that's false. So there is a way to recognize whether you are actually going to need or possibly have an extraneous solution. Hopefully you notice there that there's an x on the left. There's an x on the right. We only got one answer in this equation. There was only one variable. We only got one answer in this equation. There was only one variable. We only got one answer in this equation. There was only one variable. Okay, so I think you can see what I'm going for here is that if you have more than one variable, you must check your results to be sure that you don't have an extraneous solution. And we're probably going to get one here, since this is kind of what this question is about. Okay, first step, isolate the radical. Add 5 to both sides. So now we have the square root of x plus 7 is equal to x plus 5. Square both sides, and we have x plus 7 is equal to, if you are going to square x plus 5, please don't forget that it is not equal to x squared plus 25. No. Okay. When you square x plus 5, you must FOIL x plus 5 times x plus 5, and so it's equal to x squared plus 10x plus 25. Right? X plus 5 times x plus 5, first, outside, inside, last. Don't forget that middle term, that 10x. Okay, this is good. I got the radical to go away. I got the square root to go away. Now I see that I have a x squared, which means I have a quadratic, which means that I should set it equal to 0. Subtract 7 from both sides. Subtract x from both sides. And so we have 0 is equal to x squared plus 9x plus 18. And we can factor this and use the zero product property. So factoring this, the two numbers that multiply to 18, when I add them together, I get 9. That's x plus 3 and x plus 6. Okay. All right, great. So that means that x is equal to -3 and x is equal to -6. Okay, now here's a hint. One of them is right, one of them is wrong. Only way to tell is to plug them in. So if I plug -3 in, I get, if I plug -3 in right there, let's get rid of these 5s. Okay, so if I plug -3 in, I get the square root of 4 minus 5 is equal to -3, right? I got to plug x in there and there. Well, that's 2 minus 5. Is that -3? Yes, it is. This one works. Let's check -6. They could both work. It's possible. Okay, so let's plug in -6. Okay, so -6 plus 7 is the square root of 1 minus 5. Whoops, minus 5 is equal to -6. -1 minus 5 is -4. Is that equal to -6? No, it is not. Okay, so that means -3 works, but -6 does not. It is an extraneous solution. It is an extra solution. It is not part of this solution. Let's try another one. We got a problem here. So let me rewrite it down here. So we have the square root of 5x minus 1 plus 3 is equal to x. I'm going to subtract 3 from both sides to start. 5x minus 1 is equal to x minus 3. Squaring both sides gives me 5x minus 1 is equal to, don't forget the middle term, x squared minus 6x plus 9. Okay, add 1 minus 5x. Why do I do this? Because I want to set it equal to 0, so that way I can factor and use the zero product property. That's minus 11x plus 10. And we get factors of 10 that add to 11. That's x minus 10 and x minus 1. So x is equal to 10 and x is equal to 1. Now I have to check them. So 10, plug in 10 for x. That's 50 minus 1 is 49. Square root of 49 is 7 plus 3 is 10. That works. Okay. Next, a 1. 5 minus 1 is 4. Square root of 4 is 2. What am I putting in here? 1. Okay. Square root of 4 is 2 plus 3 is 5. That does not work. Extraneous solution. Okay. And you can actually see this, right? We're studying algebraic methods of solving square root and radical equations. If we were to actually graph, we're back to this problem. If we were to actually graph these two, plugging them into Desmos, right? I could see my line of x and my curve of x plus 7 minus 5. Okay, you can see that they only cross at one spot, which is the answer. They only cross at -3 and not at -6 right there. Okay, so we can clearly see this has one solution, but see that it is possible for it to have two, right? It's possible for this line to cross this curve somewhere twice. Okay, right? In fact, right there, right? This could be, if the curve was a little bit over, it would cross on both of these two places. So it is possible to get two answers. It's possible to get no answers. Okay, these curves do not cross at all. So when you're checking for extraneous solutions, don't just expect only one. Expect anything to happen. Okay. Next, if an equation contains two radicals, two terms with rational exponents, right? We're going to isolate one of them, eliminate it, isolate the next one, and eliminate that, and we're going to do it separately. Okay? It's probably a better idea to isolate the more complicated radical expression first, and then simplify the expressions before getting rid of the second one. Something like this. Okay, so I have to choose one of these two to isolate. 2x plus 1 looks more complicated than the square root of x. So basically what I'm going to do is I'm just going to add the square root of x to both sides. So here's my new equation. 2x plus 1 is equal to 1 plus square root x. Okay? Now I square it. That is one term. Everything is underneath the radical. The radical just goes away. This is not one term. It is a binomial expression. Don't forget you have to FOIL this and get a middle term. Okay? So 1 plus the square root of x times 1 plus the square root of x. First, 1 outside 1 radical x, inside 1 radical x, which is 2. And then last, the square root of x times the square root of x is just x. Now, there's nothing squared. I don't want to set it equal to 0. I want to get that radical by itself again, and then square both sides again, right? So I'm going to have to do this whole thing over again. So basically what I want to do is this. Subtract out the 1, they go away. That's great. Subtract out the x. So now I have x is equal to 2 times the square root of x. I could divide out the 2, but then I get a fraction. Better just to square both sides, get rid of the radical. So that's x squared is equal to, you have to square both things inside the parentheses. Okay, so that turns into 4 times x. Now I have x squared. So now I can set this equal to 0 and factor it. This is very simple to factor, but it sometimes escapes everybody, right? All you can do is take out a common factor. So x would be equal to 0, and x would be equal to 4. Okay? And check both your answers. If x was equal to 0, that's this, whoops. If x was equal to 0, that's the square root of 1, which is 1, minus 0 is 1. So that works. That doesn't mean the other one doesn't, okay? 2 times 4 is 8, plus 1 is 9, so that's the square root of 9, minus the square root of 4. So that's 3 minus 2 is 1. They both work. Okay, so it is possible that both of these things work. Okay, let's try a got a problem. Again, isolate the more complicated radical. So I'm going to add the square root of x to both sides. So we have 5x plus 4 is equal to 4 plus the square root of x. Squaring both sides gives me 5x plus 4 is equal to 16, 4 squared, plus 8 radical x, the middle term, plus x. Okay, so I'm going to do this. I'm going to subtract the 16 from both sides. I'm going to subtract the x from both sides. So I get 4x and a negative 12 equals 8 square root x. Okay, now I have a couple choices here. I could divide out the 8, but I'm going to be left with fractions. Much easier just to do this, divide out a 4. So now we have x minus 3 is equal to 2 square root x. A little bit easier to deal with without having the fraction. Oh, whoops. Okay. So now, however, that when you square both sides, you have another binomial that you have to deal with. So that's x squared minus 6x plus 9 is equal to 4x, the 2 squared and the square root squared. Now I have something to the second power, set it equal to 0, x squared minus 10x plus 9 is equal to 0, which factors, the factors of 9 that add up to 10 are 9 and 1. So x is equal to a positive 9 and x is equal to a positive 1. Don't assume that they are both correct. 5 times 45 plus 4 is 49. Minus, let's get rid of this, minus the square root of 9. Is that equal to 4? That's 7. Minus 3, which is 4. That's good. Okay, so this one works. And 5 plus 4 is 9, so that's the square root of 9 minus the square root of 1. That's 3 minus 1 is not 4. So this one has an extraneous solution that makes the problem not work. Last one, a little bit harder. Now instead of just having one term underneath the radical, we have a binomial radical expression for both terms. Okay, so we have the square root of 3r minus 8. I'm just going to take this one and add it to both sides. So we get 1 plus the square root of 9 minus 2r. Okay, squaring both sides gives me, it's going to be a little long, so squaring both sides gives me 3r minus 8. This is a binomial expression on the right. You do have to FOIL it together. So 1 plus 2 of these radicals plus the last term squared, which the radical just goes away. Okay, so not too bad. Just make sure you don't forget the middle term. All right, so we're going to subtract 1 from both sides. We're going to subtract 9 from both sides. Okay, we're going to add 2r to both sides. Okay, so we get 5r. So that's 8 and 1 and 9 give me minus 18 is equal to 2 times 9, 2 times 9 minus 2r. Okay, unfortunately now it's a problem because the 5 and the 2 do not divide. So that means I'm going to have to square both sides of these, and the numbers are going to get a little bit out of control. Okay? But we can do it. We can deal with it. Okay? So this becomes 25r. 18 times 5 times 2 gives me minus 180, 25r squared, 180r plus 18 squared is 324. And that's going to be equal to 4 times 9 minus 2r. Square the 2, square the square root, and the square root part goes away. Okay, so rewrite this, 25r squared minus 180r plus 324. 4 and 9 give me 36 minus 8r. I have an r squared, so subtract 36 from both sides. Add 8r to both sides. Minus a 36 here, setting this equal to 0. So we have 25r squared minus 172r, and 324 minus a 36 gives me 288. So now the trick is to find the factors of 288 and the factors of 25 that add together to give you 72. If you can't figure that out, if that factoring is too difficult for you, you can always use the quadratic formula, or you could use a graphing calculator to help you graph it. Okay, I'm just going to use my calculator. And get that x is going to be equal to 4 and x is going to be equal to 72 over 25. Okay, which means that this would actually factor to something like r and 25 are 4, and both of these are going to be minus, and 72. Ooh, 72. I believe that should work. 4 times 72 is 288. 172 together, the inside pair and the outside pair, give me 172. So now it's just a matter of plugging both of these numbers back in and seeing if they both actually work. The 4 is easy to plug in. So 3 times 4 is 12 minus 8. Oh, whoops. 12 minus 8 is 4. So that's the square root of 4 minus, what am I plugging in here? I'm plugging in 4. 9 minus 8, 1. So that's 2 minus 1. So that works. So this one is good. Plugging in 72 over 25 is not necessarily going to be that fun. 3 times 72 over 25 minus 8 would give me 16 over 25, which would be, the square root of that would be 4 over 5. And 9 minus 2 times 72 over, 72 over 25 gives me 81 over 25, which would be 9 over 5. And that would actually give me a -1, not a +1. So that actually doesn't work. Okay, so the answer to this would have just been 4. So this is obviously the more complicated type of problem that you would get, where you have two variables with a binomial, or two radicals with a binomial under each radical. This one is a little simpler because at least this one is by itself, and then these are even easier because there's only one radical in there. And then the original problems that we did should be a little bit more straightforward. Okay, so again, easier, one radical, and all of these are on the sort of the a little bit easier method. Just scanning through these, none of them will have extraneous solutions. How do I know? Because in each case, each one of these only has one radical. This one probably has an extraneous solution. Okay, and you should notice that this was similar to solving an absolute value equation, right? Isolate the thing, isolate the radical, get it alone, and then do something to make it go away. In an absolute value equation, we split it into two parts. Here, we just raise everything to a power. Okay? And that was 6-5, solving square root and other radical equations.